Right, so we go on to the last model of the atom today, wave mechanical model. Before this, what did we do? That Bohr's model was given a serious blow due to de Broglie relationship, which gave us the dual nature of matter, that electron, it behaves as a wave as well as a particle. And then Heisenberg uncertainty principle also gave a serious blow to the Bohr's model. Therefore, a new model that was suggested, which was known as the wave mechanical model of atom, and this wave mechanical model of atom, it gave us or explained us both the wave as well as particle character of electron and the atom. Okay, so when we are doing the wave mechanical model of an atom, this model that was proposed by Erwin Schrödinger. This was the scientist who proposed this model, and the model, it describes the electron as three-dimensional wave in electronic field. Three-dimensional wave in electronic field of positively charged nucleus. Of positively charged nucleus. Now, because it was behaving as a wave, therefore he suggested a function which was known as psi, and this psi that was considered as the amplitude function. It was considered as the amplitude function. Schrödinger also proposed an equation to explain the value of psi, and this equation is known as the Schrödinger wave equation. The equation is explained in three different coordinates, x, y and z. So we have d square y upon dx square plus d square y upon dy square plus d square y upon dz square, where x, y and z, there are the three coordinates, plus 8 pi m square, 8 pi m square upon x square, e minus b psi, that is equal to 0. Right? So this equation, although it's very difficult to explain this equation, but still what we can gather from this equation is the function of psi. Okay? So when he discussed about psi, over here we have m, which is the mass of the electron, h is the Planck's constant, E, that is the energy associated with the electron, and V is the potential energy of the electron. V over here is the potential energy of the electron, and psi, that is known as the wave function. Right? Now when he calculated or gave us a calculation about this, he also gave us a significance of psi. What does psi suggest? He gave us significance of psi. So what did he say? That the wave function psi, that is related to the amplitude of the wave, it's related to the amplitude of the wave in terms of coordinates x, y and z. Okay, so it was the amplitude of the wave in x, y and z coordinates in all the three dimensions, and it may have positive as well as negative values. The psi over here may have positive as well as negative values. Okay. But Schrodinger's main aim was to calculate the probability density of an electron which is never negative. Okay, but as you can see over here that psi had a value positive or negative, therefore psi could not be taken as the probability density. So another term was suggested which was psi square, right? The square of amplitude of wave. This particular function, that is the psi square, that was known as what? It was known as the probability factor. It was known as the probability factor, and this gave us the probability of finding an electron around the nucleus, which was defined as probability density. So psi, it was unable to give us the probability density, but the square of psi that gave us the probability density, telling us where the electron is present around the nucleus in a small space. Okay, so these were the two factors which he gave, and this probability density gave us the small space in which the electrons they are found, and another term was suggested which was known as orbital. So what is an orbital? Bohr suggested orbit, which was elliptical orbits or elliptical paths on which the electron was revolving around the nucleus, but Schrödinger gave us the word orbital. Orbital is the three-dimensional space where the probability of finding an electron is maximum. Probability of finding an electron is maximum. Okay, so next to orbit, when we are describing the wave character, the new term orbital came into being, which was a three-dimensional space where the probability of finding an electron that was maximum. Okay, now Schrödinger also suggested to us 4 numbers. To give the exact location of the electron, which were known as quantum numbers, which we will discuss in the next session. Okay. Also, there were certain spaces where probability of finding an electron was 0. Right? And this space or point or plane where the probability of finding an electron is 0, this was known as node. The point where the probability of finding an electron is 0, that is known as node, and the plane where the probability of finding an electron is 0, that is known as the nodal plane. Okay, now when we are talking about hydrogen, then for hydrogen wave functions, there are different kind of nodes which are present. There are different kind of nodes which are present. The first one that is known as radial nodes. If you get a question on calculating the radial nodes they are equal to n minus L minus 1. Right? Where n that is going to be the principal quantum number which we will discuss later. L that is the azimuthal quantum number minus 1 that gives us the radial nodes. Okay. The number of angular nodes. The second type of nodes which we have, they are the angular nodes, and the angular nodes they are given by L, azimuthal quantum number. Right? So if you want to calculate the total number of nodes will become n minus L minus 1 plus n. Right? So this and this gets cancelled. Total number of nodes, that is going to be equal to n minus 1. Right? And nodal planes, that is always equal to L. Okay, so let's say that Schrodinger suggested that there are 4 kind of orbitals present. Okay, later on it was suggested that there was 4 kind of orbitals present. The first one was S, P, D and F. So we need to calculate the total number of nodes for each of the orbitals. Let's say we are calculating for S orbitals. So let's calculate the number of nodes for S orbital. When we are calculating for S orbital, there are n minus 1 radial nodes, okay, and there are no angular nodes. So there are 0 angular nodes over here. So total number of nodes that will become equal to n minus 1. Okay? Then for p orbitals, when we are calculating for p orbitals, there are n minus 2. There are n minus 2 radial nodes and there is 1 angular node. So what is going to be the total number of nodes over here? N minus 2 plus 1, that becomes equal to n minus 1. N minus 1 total nodes. Right? Then for d orbitals, the radial nodes they are going to be n minus 3. Right? And there are 2 angular nodes. So again the total number of nodes in this case, that will also become equal to n minus 1. Right? So when we are talking of total number of nodes, either it is for s orbital, let's say that we are saying that the electron that is present in n is equal to 3. Then total number of nodes in the s orbital, that will be equal to 3 minus 1, that is equal to 2. Okay? So total nodes once can be calculated by the same formula for all the orbitals, that is n minus 1. Clear? But over here, For s orbital there are n-1 radial nodes and there is no angular node. This you have to remember. For p orbital there is n-2 radial nodes and there is only one angular node, and for d orbitals there is n-3 radial nodes plus 2 angular nodes. Right? Also Schrödinger gave us the operator form. So what is the operator form of Schrödinger wave equation? The operator form that is given as H psi, that is equal to E psi, where H that was known as the Hamiltonian operator, right, and it is equal to T plus V. Hamiltonian operator which is equal to T plus V. T over here is the kinetic energy operator, and V is the potential energy operator. Okay, so the operator form of Schrödinger wave equation, that is equal to H psi is equal to E psi, where H is the what? It is known as the Hamiltonian operator. Now, as we just said that the Schrödinger wave equation, it suggested about the quantum numbers, which is a very important part of this chapter. So let's go on to the next section, which is the quantum numbers. What do we understand by quantum numbers? Quantum numbers are a set of 4 numbers which gives us the complete address of an electron. It gives us the complete address of an electron. Or we can also say 4 numbers which is required to locate any electron. That is the quantum numbers, right? So we have 4 quantum numbers. The first quantum number is the principal quantum number, which is denoted by n. Right? And this quantum number was proposed by Bohr. Now over here, this quantum number n, it denotes the principal shell or orbit in which the electron that is going to be present. Okay. Now when we are looking at the values of n, if n is equal to 1, then the orbit in which the electron present, that is going to be equal to k. If n is equal to 2, L. If n is equal to 3, M. If n is equal to 4, N, and so on. Okay. Now from this principal quantum number, which all other values can be calculated? The first one is we can calculate the number of subshells present. Number of subshells present. The number of subshells present, that is given by n square. Okay, subshells, or you can write, rather than subshells, you can write the number of orbitals present. Don't write subshells, write the number of orbitals present. Right? For example, if we are talking of n is equal to 1, the number of orbitals present, that will be equal to 1, right? If n is equal to 2, then the number of orbitals present, that will be equal to 4, and so on. Okay? Then it also helps us to calculate number of electrons present in the main shell, and it is given by 2n square, right? For example, if we get a question, what are the number of orbits present in n is equal to 3? So the number of electrons present in n is equal to 3, that is going to be equal to 18 electrons. So when we are talking of the third orbit, the number of electrons, that is going to be equal to 18. It also gives us the value of angular momentum, which can be calculated as mvr is equal to nh upon 2 pi, where n is the principal quantum number, m is the mass of the electron, v is the velocity of the electron. This whole is known as the angular momentum. Okay? And we know when we did the Bohr's atomic theory, this entire thing that was giving us the quantization of angular momentum according to Bohr, in which he said that only those orbits are permissible which have an integral value of h upon 2 pi. Okay? Then this quantum number also gives us the energy associated with each electron. We have also done this before. The energy associated, that is equal to minus 2.18 into 10 raised to power minus 18 upon n square into z. Okay? And the unit which we use over here, that is joules per atom. Right? It also gave us the energy in electron volts, minus 13.6 upon n square into z. Z है कि z square into z square electron volt per atom, and also in kilojoules per mole, which is minus 1312 upon n square into z square. Kilojoules per mole, right? And we also know when we are talking of the energy, we say higher the value of n, higher is going to be the energy. Okay? Although over here we can see that this is inversely proportional, but still there is a negative value associated with it. So higher the value of n, higher is going to be the energy, which means as the electron is moving away from the nucleus, the energy that is going to increase. So the energy in the first orbit, that is going to be least, then the second orbit, then the third orbit, then the fourth orbit, and so on. Clear? Okay. Then principal quantum number also gives us the radius. It gives us the radius of the orbit, of the nth orbit, which is given by 0.529 into n square upon z angstrom. So as the value of n will keep on increasing, the distance of the electron from the nucleus also keeps on increasing. Okay? Is it clear? So this is what the principal quantum number it gives us about any electron which has the value of n which is prescribed. Okay, then let's go on to the second one, the second quantum number, that is azimuthal quantum number. The second number that is known as azimuthal quantum number. Azimuthal quantum number is denoted by L, and the scientist who proposed this, his name was Sommerfeld. This quantum number is also known as angular subsidiary or secondary quantum number. Right? Now this quantum number has the value n-1. Okay, and it gives us the number of subshells present in the main shell. If the value of L is equal to 0, then the subshell present is S. And S over here means sharp. Okay? The S over here, it means sharp. If L is equal to 1, the subshell present is P, and P over here means principal. Okay? If L is equal to 2, the subshell present, that is going to be D, and D over here means diffused. And if L is equal to 3 for 3, the subshell present is F, and F over here means fundamental. Right? And last, which is hypothetical, if L is equal to 4, the subshell present is G, and G over here means generalized. Okay, now let's illustrate the value of the relationship between value of L and N over here. We say that the value of N that is equal to 1, right? In that case, the value of L will be equal to 0 and the subshell present will only be S. Okay? If L is equal to 2, L can have two values, 0 and 1. Anything, because we can see over here that the value of L that is equal to n-1. So it has to be less than n. Okay? So we have n is equal to 1, L is equal to 0, S. If L is equal to 2, L is equal to 0 and 1, and the subshells present are S and P. If the value of n that is equal to 3, then n is equal to 0, 1 and 2. And the subshell present is S, P and D. Right? And if n is equal to 4, n is equal to 0, 1, 2 and 3, and the subshell present would be S, P, D and F. Now this data suggests that when n is equal to 1 cannot have P, which means 1P does not exist, or 1D does not exist, or 1F does not exist. In a similar manner, when we go to 2, then in case of 2, P can exist, but D cannot exist, 2D will not exist, and 2F will also not exist. Right? When we go to n is equal to 3, so 3S, 3P and 3D exist, but 3F will not exist. For n is equal to 4, all the 4, S, P, D, F, all of them they are going to exist. Okay? So this is what the subsidiary quantum number is. Now subsidiary quantum number, also it was suggested that when we are talking of energies of the various subshells, then S had the least energy, P, D and F. This is how the energies it kept on increasing, and it helps us to calculate the angular momentum, MdR, that is equal to under root of L plus 1 H upon 2 pi. Okay, clear? It also helps us to calculate the number of electrons in the subshell, which is given by 2L plus 1. Right? Sorry, not number of electrons, these are number of orbitals. Okay? And when we are talking of number of electrons, that is going to be given as 2L plus 1. For example, if we want to calculate the number of electrons in S, number of orbitals in S, then the number of orbitals would be 2 into 0, because the value of L is 0, plus 1. Only one orbital is present in S. If we want to calculate the number of orbitals in P, for P, the value of L, that is equal to 1. So 2 into 1 plus 1, that is equal to 3. If you want to calculate the number of orbitals in D, then that will become equal to 2 into 2 plus 1, that is equal to 5. And in F, 2 into 3 plus 1, that is equal to 7. So therefore, S has only one orbital, P will have 3 orbitals, D will have 5 orbitals, and F they are going to have how many? 7 orbitals. Okay, then the third quantum number which we are going to do, that is magnetic quantum number. Magnetic quantum number, that is denoted by ML, and the scientist who suggested this was Langley. Now the magnetic quantum number, basically it gives us what? We had seen that the Bohr's model failed to explain the Zeeman effect, right? But the magnetic quantum number, it explained the Zeeman effect, that is splitting up of spectral lines when they are kept in the magnetic field. So magnetic quantum number gave us an appropriate reason of magnetic splitting, which is known as the Zeeman effect. Also the magnetic quantum number, it gave us that under the influence of magnetic field, each subshell is further subdivided into orbitals. They are subdivided into orbitals. Okay, and it describes the orientation and distribution of electron cloud. Clear? Now the value of L that ranges between minus L, 0 and plus L. Okay? ML that is equal to minus L, 0 plus L. So when we are talking of, let's say, if the value of m will also be equal to 0. Okay, now if the value of m is equal to 0, it means that for this orbital, the orientation is going to be same in all the three coordinates. Therefore, we know that for n is equal to 0, the orbital present is s, right? And for this subshell, we say that it is non-directional. Right? We say that it is non-directional. Why? Because the value of 0 for m suggests that it has the same orientation in all the three coordinates. So it will have the same orientation in all the three coordinates, then it has to be non-directional. Clear? Okay. Then the last quantum number which we are going to suggest over here, that is the spin quantum number. Spin quantum number. Now, spin quantum number, that is denoted by ms, and it was proposed by Gram-Smith. The spin quantum number can have only two values, plus half and minus half. Right? Where we say that when we are talking of plus half, it means that the electrons, that is rotating clockwise, and if the value is minus half, then it is anti-clockwise. Right? And then when we are talking of spin quantum number, it gives us the value of angular momentum. Denoted by mu s. Mathematically, mu s, that is equal to under root of s plus 1, right? Where s over here, that is going to be equal to number of unpaired electrons, right? S, that is equal to number of unpaired electrons. Now in this case, there is another very important thing which you can get to calculate: spin multiplicity. Which is known as the spin multiplicity. The spin multiplicity, that is calculated by 2 into summation of spins plus 1. Right? Let's illustrate by taking the example of carbon. When we are taking the example of carbon in the ground state, the electronic configuration in this case is 1s2, 2s2 and 2p2, right? So we are saying that this is 1s2, 2s2, 2p2. Okay, when we are talking of the electronic configuration in the excited state, one of the electron jumps from here to here. So we will have 1s2, 2s1, 2p3, right? Now over here there are 1, 2, 3, 4, 5 electrons which are spinning clockwise, right? And there is one electron which is spinning anti-clockwise. So in order to calculate the spin multiplicity formula over here? Plus 1. So when you calculate this, this will become equal to 2 into pi by 2 minus 1 by 2 plus 1. ठीक है? So this will become equal to 5 minus 1, that is equal to 4 by 2. That becomes equal to 2. 2 into 2 plus 1, that is equal to 5. So spin multiplicity for the carbon atom, that is equal to 5. ठीक है? So you understood till here? Okay. Now today we do only till here the quantum numbers. Tomorrow we are going to finish this chapter by doing the shapes of orbitals according to the Schrödinger wave equation, and then the last, which is the electronic configuration. Okay?